Let's switch now to physical water problems. I'm only going to talk about total suspended solids, the total amount of particles that are in a water sample. There are rough guidelines. They depend, and it all depends on the application of the water, whether it's 20 parts per million, 100 parts per million. You're going to see different thresholds in different situations. Once you're up at 100 parts per million, you're going to be clogging emitters, no question. And the other thing about these suspended solids is that let's say you're chlorinating or using ozone, then those oxidizers are going to react with the peat or soil rather than with the pathogens. Okay, there's a lot of demand from the water before that sanitizer can even find and attack the pathogens in the water. Okay, and even with something like copper ionization, the copper will also bind somewhat to the peat. So the key with physical contamination is filtration. And we've got a research program that Dale Haskell and my team has been doing, looking at suspended solids before and after different kinds of growing media, different kinds of filters, sorry. So here we've got a paper filter, a rolling paper filter, and it's got samples before and after that water has passed through the filter. And you can see that in this case, we've got a reduction of about 50% of the particles from the filtration. Now, we can measure total suspended solids. We can also send a sample off to a lab, and I would talk with your filtration supplier to get a recommendation from them, and they can look at different diameters here in the x-axis, the horizontal axis, and percent of the particle volume in your suspended solids that are at these different sizes. Okay, so here we've got 3 different locations, and this is their irrigation water before it went through the filtration system. And you can see that we've got roughly 50% of the particles were bigger than 150 microns, and 50% of the particles were less than 150 microns. Okay, what's a micron? Well, to give you an idea, 500 microns is half a millimeter. Okay, and so that would be about a 50th of an inch. So depending on the size of the holes in your filter, it's going to take out more or less of the particles. Here's some units you might be familiar with: mesh size, microns, and then some notes about them. So we said 150 microns was about the median diameter of suspended solids we saw in irrigation water from several nurseries. It corresponds with a 100 mesh screen. Fine sand would be taken out with a 60 mesh screen. It's about 1/4 of a millimeter, or 250 microns. And so the finer the screen that we have, unfortunately, the less water flow volume that we're going to get through, but the smaller the hole and the more of the particles we'll take out. And if we think about filtering biological material, well, we might be filtering out big chunks of algae with these filters, but bacteria, zoospores of Pythium Phytophthora are going to be smaller even than this type of a screen. So we're talking about membrane filtration, which are much smaller holes to be able to remove biological contaminants. Here we've got an example of one of these paper filters. The water comes down, it gets trapped on the paper, and as the paper gets filled up the pores get filled up with soil, then it moves along. And here's an example of work Dale did, just looking at, under a microscope, different papers that are used in these paper filters. And here you can see a paper from one greenhouse with very big holes. Okay, so that distance from there to there would be 250 microns, for example. Okay, whereas this is from a different greenhouse with much smaller holes. So this grower is going to go through less paper, but is going to have most of the particles pass through. This grower is going to have more cost in paper, but would be more effectively filtering.